In the last lecture, we have discussed about the memories, RAM and ROM. As far as ROM is concerned, it is a read-only memory and it is a combination of a decoder and OR gates. So now let us discuss about the type of ROMs. The required paths in a ROM may be programmed in 4 different ways, and the way how the ROM are programmed, and these are the types of the ROMs. The first is mask programming ROM. In this, the programming or the masking is the programming or the fusing is done at the time of the fabrication. Means when we are fabricating a ROM or we are manufacturing a ROM, at the time of the manufacturing, the programming is done. That is called a mask programmable ROM. Another is read-only memory or PROM. That means here is the fuses. So end user can program the ROM as per its requirement, and what we have done in the last example, that is called PROM, programmable read-only memory. Another is erasable programmable memory, that is EPROM. It is placed under a special ultraviolet light for a given period of time, and which will erase the pattern of the ROM, and we can reprogram the ROM just like a PROM. So in this EPROM, we can erase just like a rewritable CD. So we can erase the CD and we can burn the CD. The burning process is called fusing. So this is the type of ROM, that is EPROM. We can erase and we can reprogram the ROM. Now another one is electrical erasable programmable ROM, EEPROM, and it is erased with an electrical signal instead of the ultraviolet ROM. Now in case of the EPROM, the erasing is done with the help of ultraviolet light, while in the case of EEPROM, the erasing is done with the help of electrical signal instead of the ultraviolet lights. So these are the 4 types of ROM: mass programmable, PROM, EPROM, and EEPROM. Now comes the random access memory, that is the RAM. A memory unit stores binary information in groups of bits called word. 1 byte is 8 bits and 1 word is equals to 2 bytes. So we can say a 16-bit is equals to 1 word. The communication between a memory and its environment is achieved through data input and output lines, address select lines, and control lines that specify the direction of the transfer. Means if we are reading or we are writing. When we are writing, then the data will be into the memory, and when we are reading, data will be out from the memory. So this is the block diagram of a RAM. We have K address lines. We have a read, a write. These are again input, which will decide that if we are reading or we are writing. We have n-bit data input and we have n-bit data output. So the size, the n-bit will be decided that it is a 8-bit memory or it is a one word memory. When it is a 1 word memory, then the size n-bit will be 16 bits. So in that case, n equals to 16. Now the computer or the processor you are using, that is a 64-bit. So in that case, we can say that the input line is of 64-bit and the output line is of 64-bit. So this decides the size of the processor decides, or the data line decides what is the size of the ROM. The content of a memory: each word in memory is assigned an identification number called an address. starting from 0 up to 2 raised to power k minus 1, where k is the number of address lines. Again, we are using a decoder here. So with the help of the decoder, we have k is to 2 raised to power k decoder, and the output line or the address lines will be 2 raised to power k, which will range from 0 to 2 raised to power k minus 1. The number of words in a memory with one of the letters k equals to 2 raised to power 10, that means 1k, m equals to 2 raised to power 20, that is megabyte, g equals to 2 raised to the power 30. So we say if we have a 64k, then it is 2 raised to power 16. 2 MB means 2 raised to power 21. If we say 4GB, then it is 2 raised to power 32, because G is 2 raised to power 30 and 4 equals to 2 raised to power 2. So these are the memory representation, how the size comes for a particular memory. So here are the some example of 1K of memory. The memory content, these are the arbitrary what we are reading or writing. So this is the size of the word, 16-bit, and these are the address locations 0 to 1024. 2 raised to power 10 is 2 raised to power 10 is 1024. So for a 1K memory, the locations are ranging from 0 to 2 raised to power 10 minus 1, that is 1025 1023. So it starts from 0 to 1023, that is a 1K of memory locations, and each memory location has 16 bit of word. That means 16 bits are either input or output from the memory. Now how the read and write operation takes place. Transferring a new word to be stored into memory. When we are reading, when we are writing, now apply the binary address of the desired word to the address line. First, we have to select the particular address line at which location we have to read or we have to write. Then apply the data bits that must be stored in the memory to the data input line. So first we have to select the address, then we have to put the data on the data lines, then activate the write input. We have two inputs, read and write. So we have to activate the write input. Now that was the process of writing into the memory. Now when we are transferring a stored word out of the memory, that means when we are we have to read the memory location. The same, first we have to go to the address lines. We have to select the address line, then we will go to the particular binary address, then activate the read input. The commercial memory sometimes provide the two control inputs for reading and writing in somewhat different configuration in table 7.1. The table number is from your textbook, Morris Mano. So here we say whenever memory enable is 0, now whatever is the read write. So here we are using a chip enable, that is another input. When it is 0, then memory operation will be none. Means whatever is the value either 0 or 1 of the read write. So here read oblique write, we are using a single input for the read write. So whenever enable is 0, the no operation takes place. Whenever enable is 1, now it will check for the read write input. Whenever it is 0, then write to the selected word. Whenever it is 1, read from the selected word. So select word is selected from the address lines. So for the 0, if the read write button read write input is 0, it will write. When it is 1, it will read. So we say the read oblique write bar. So this the input will be like this. Now in random memory, the word locations may be thought of as being separated in space, with each other occupying one particular locations. In sequential random access, that means randomly we can access any memory location depending upon the input address lines. So if we have to go to the 1023 location, then we can directly go to the 1023. And in sequential access memory, just like your magnetic tapes, the information stored in some medium is not immediately accessible, but it is available only certain intervals of time. A magnetic tape or magnetic disk is a type of sequential access memory. So these are the type of memory depending upon the access of the memory. So we have a random access memory and we have a sequential access memory. Now in the unit 2 we'll discuss about the sequential access memory when we will be discussing the shift registers and flip flops and the counters. In case of the random access memory, you can directly give the address. Suppose you have to go to the location number 9. So the input will be 1001. So whenever the address line is 1001, then it will directly go to the address line 9, and we can either read and we or write depending upon the value of the read write input. Now in a random access memory, the access time is always the same regardless of the particular location of the word. So whatever is the address, either it is 0, either it is 1024, so the access time will be same. On the other hand, in a sequential access memory, the time it takes to access a word depends on the position of the word with respect to the reading head position. Suppose the reading head is at 0th position. Now it will take less time to go to the first position and it will take more time to go to the 1023 location. Means for the first location it will take some time because it will move from the first location to the last location sequentially. So in sequential access memory, the time it takes to access a word depend on the position of the word with respect to the reading position head. Therefore, the access time is variable depending upon the address to address. Static RAMs, there are two type of RAMs, SRAM and DRAM. First is the static and another one is the dynamic RAM. So let us take a quick look on the static RAM. SRAM consists essentially of internal latches that store the binary information. Now, what are the latches? We're going to discuss in the unit 2. The stored information remains valid as long as power is applied to the unit. SRAM is easier to use and has a shorter read or write cycle, means it is faster as compared to the DRAM. Now the characteristics, it has low density, low capacity, high cost, high speed, high power consumption. So these are the characteristics of static RAMs or SRAM. Low density means it takes more space. Low capacity means it can store less data. Cost is high. Speed is high, means it is fast. So whatever device is fast in electronics, that will cost high. And high power consumption, it consumes more power. Now the dynamic RAM or the DRAM stores the binary information in form of electrical charge on a capacitor. The capacitors are provided inside the chip by the metal oxide semiconductor transistors. The capacitors tend to discharge with time and must be periodically recharged by refreshing the dynamic RAM. So we say that in the dynamic RAM, refreshing is required, and the reason behind the refreshing is that the information is stored in the capacitor. So there is a leakage in the capacitor. That's why we need to refresh the dynamic RAM. The advantage is DRAM offers reduced power consumption and large storage capacity in single memory chip, means it has high density. High density, high capacity, low cost. Whenever density is high, then the cost will be low. And the cost is low, that means speed will be low and it consumes less power as compared to the SRAM. So these are the characteristic differences between SRAM and the DRAM. Now again, the classification of memories. Memory units that lose stored information when power is turned off are called volatile memories. Both SRAM and DRAM are of this category since binary cells need external power to maintain the stored information. So we can say SRAM and DRAM are the volatile memories. The non-volatile memory, such as magnetic disk, ROM, retains its stored information after removal of the power. So the ROM and the magnetic disk are the non-volatile memory. So depending upon the volatility of the memory, there are two types of memory. First is volatile memory, that is SRAM and DRAM, and another one is non-volatile memory, that is magnetic disk and your ROMs. Now come to the combinational programmable logic devices. There will be a question from the PLDs in your exam, and the question will be of about 10 marks. A combinational programmable logical device is an integrated circuit that programmable with programmable gates divided into an AND array and an OR array to provide AND or sum of product implementation. So it will be structure will be like what we have studied in ROM. ROM has decoder. Decoder is nothing but it is an AND gate, AND array, and at the output we have an OR different types of OR gates. So it's an OR array. So the combinational PLDs are nothing but it implements sum of products, and it is an AND OR arrays. Now the way in which these arrays are arranged, depending upon that, we have different type of programmable logical devices. Now first is the PROM, what we have studied. Fixed AND array constructed as a decoder and programmable OR gate. So the work of the decoder is to provide 2 raised to the power n AND terms, that is the product terms, and OR gate are used to sum them product term. That is the PROM. We have PAL, programmable array logic, which has programmable AND array and fixed OR array. In case of PROM, AND array is fixed. In case of PAL, OR array is fixed. And the last one we have PLA, programmable logic array. Both AND and OR arrays are programmable. So these are the major differences. In PROM, AND array is fixed. In PAL, OR array is fixed. And in PLA, both arrays are programmable. So here are the block diagram of PROM, fixed AND array, programmable OR array, and the AND array is nothing but the decoder. In PL, programmable array logic, programmable AND array, OR array is fixed. And we have PLA, programmable logic array, and programmable OR array programmable. So the both arrays are programmable. As we have already studied the PROM, we will directly come to the PLA, programmable logic array. Now, when you are going to design a PLA, you have to construct a PLA table. So, when you construct the PLA table, now the work is of the manufacturer, who will fuse or who will burn the table into your array, and it will be programmed. So, the burning process is called fusing process. That is that you done in your CD. To write a CD, the process is known as burning the CD. So in the same way, you have to construct the programmable PLA table, and that table is provided to the manufacturer, and it burns the PLA as per your requirement. So let us take a quick look on the PLA, how it looks like. As we have discussed in the decoder, in the PROM is replaced by an array of AND gates that can be programmed to generate any product term of the input variable. So here we need not to construct n to the power n AND term. In case of the PROM, whenever we are using decoder and we have n number of inputs, then 2 raised to power n are the output. That is the advantage of PLA, that we can program the AND array, and we can use only such type of array minterms which is required. We need not to generate all minterms. The product terms are then connected to OR gates to provide the sum of product for the required Boolean function. The output is inverted when the XOR gate, XOR input is connected to the 1 as XORing X and 1 is equals to X bar. The output doesn't change and the connects to 0 since X XOR 0 is X. So it is nothing but what we have studied in parallel adder subtractor. Whenever one input of the XOR gate is 1, then the output of the XOR gate will be complement of the input. Whenever it is 0, then the output will be X or the same input. That is the concept, because we are going to complement the output function. Let us discuss with an example. Suppose we have two functions, f1 equals to a b bar plus ac plus a bar b c bar, and f2 is ac plus bc whole bar. So we can say that the f1 is in true form and f2 is in complementary form, because we have f2 equals to ac plus bc whole bar. So we have to implement this particular function with the help of PLA. Now what we do, we construct the PLA programming table. We write all the product term. First product term is AB bar. Here is AB bar. Next is AC. Here is AC. A bar B C bar. A bar B C bar. We have AC. I already have written AC. We have BC BC. So we in F1 and F2 we have total 5 minterms, but taking AC as a common, we have only 4 product terms. So we need not to use a decoder 3:8 decoder, but we need to only 4 AND gates. So this is the major difference between PLA and PROM, because when we are using a decoder, then it will give an output of the 8 product terms. So here we need not 8 product terms. So we were discussing the example. There was some technical issue. So as per F1 and F2, we have made a programming table. We have write in the first column, there are the all minterms. So we have reduced AC into a one term, because it is appearing twice in also in F1 and F2. So there are 4 product terms. We have the input. We have written input as A, B, C. So in the first term, we have A, B bar. So whatever is A is 1, B bar is 0, and we have put it dash. That is a don't care about C. In the second term is AC, then 1 dash 1. Next is BC dash 1 1. We have A bar B C bar 0 1 0. Now we write the output, because F1 is in true form, we have written true T. F2 is in complement form, we have written F2 as C. So whichever term is present in F1, that will be 1. So first term is AB bar, then AC, then A bar BC. So 1 1 dash 1. Where there is a dash, there will be no fuse. Where there is a 1 and where there is a 0, these all are programmed. So again, in case of the F2, we have only 2 terms, AC and BC. So we have put it 1 1 and dash on the other locations. So when we have designed the PLA programmable table, that is enough. You can stop your question here. But the program, the structure will be look like, we have inputs A, B, C, and we have A bar, B, B bar, C, C bar. So we have all 6 lanes. We have used 4 gates, A, 1, 2, 3, 4 for the 4 product terms. So first term is A, B bar. So we have A is here and B bar is here. So where there is a cross, there is a connection. Again, next term is AC. So we have C and A. Next term is BC, C and B. Next term is A bar, BC. So here is A bar, B and C bar. So where there is a cross, there is a connection. Otherwise, it will be open circuit. And again, we have to include in that term. So F1, in F1, we have AB bar, AC and A bar, B, C bar. So there are 3 crosses. And the second term, we have AC and BC. So we have crossed here. So here it is in true form. That means the one input of the XOR gate will be 0. So whenever it is 0, then the output will be F1. So whenever in the second gate, for the second XOR gate, we have put it 1. So that means the output will be F2 bar. So this is the way how a PLA is designed. So we in the question we have to solve. We have to do the solve K-map for F1, F1 bar, F2, F2 bar. We have take the common terms, that how to minimize the number of min terms, and then we have to construct the PLA programmable table. You need not to draw the structure in the examination. Now, how to draw the programmable table? Programming table. First, list the product terms numerically. Specify the required paths between input and the AND gate. Specifies the path between AND and OR gate. For each output variable, we may have a true or a complementary for programming the program XOR gate. So whenever it is true, then the other input to the XOR gate will be 0. Whenever it is complemented, other input will be 1. Now for the simplification of how the simplification of PLA is done. Carefully investigation must be undertaken in order to reduce the number of distinct product terms. PLA has a finite number of AND gates. PLAs are commercially available in the market, so it has a limited number of AND gate and limited number of outputs. Both the true and complement of each function should be simplified to see which one can be expressed with fewer product terms and which one provide terms that are common to other function. So care must be taken into the mind when we are solving the input function with the help of K-map. Then we have to solve both for true term and the complementary term. With an example, that will be easy when we are going to discuss with the help of example. Suppose we have to implement with the help of PLA, and F1 is summation 0, 1, 2, 4, and F2 is summation 0, 5, 6, 7. So I have to solve is with the help of the K-map. For the F1, I can make for this one, this is your pair. For this one, pair will be like this, and for this one, pair will be like this. So when I am pairing ones, I am solving for true value, and it comes to be F1 is A bar B bar plus A bar C bar plus B bar C bar. Now again, when I am pairing zeros, which are the missing values, that is POS, product of sum. These are the zeros. When I pair zeros, it will give so one pair, second pair, and the third pair. It will give me the value of F1 with 0 element. So this is your F1 bar. You have to write as in case of the sum of SOP and put a bar on the, this is your F1 bar. Similarly, I can solve for F2 for ones and for zeros. Now we can see if we take F1 in complement value and F2 in true value, then two terms are common, AB and AC. So with these two term commons, that it was in the last example. In the last example, I have written directly, but when we solve this F1 and F2, so F1 will be in the complementary form and F2 will be in the true form. So both the true and complement of the functions are simplified in the sum of products. We can find same terms from the group terms of the function F1, F1 bar, F2, F2 bar. So finally, F1 is AB plus AC plus BC whole bar. F2 is AB plus AC plus A bar, B bar, C bar. So F1 is taken in the complementary form and F2 is taken in the true form. So we have to construct the PLA table, programming table. So I have put it all the min terms. First is AB, AC, BC, and A bar, B bar, C bar. These are the four product terms. For the AB, input is 1, 1, AB. 1 dash 1 AC, dash 1 1 is BC, 0 0 0 is A bar, B bar, C bar. F1 is in complemented form, I have written here C. F2 is in true form, I have written here true. Now whichever term is included F1, that will be 1. So AB, AC plus BC. Whatever term is here in the F2, that will be 1, that is AB, AC and A bar, B bar, C. Now you can stop your question here because in the PLA programming, you have to make the PLA programming table. Further, we can implement this function like this. So again, at the input will be A bar, B bar, C bar. We have used an OR gate, and again we have used an XOR gate. For F1, it is in complemented form. So the next input to the F1 is 1, and here input will be 0. Oh, the next is PAL. I think we should stop our class here. In the next lecture, we're going to discuss the programmable array logic.